Thank you so much for the kind invitation. It's a pleasure to be here. I want to thank especially Professor Cermak for inviting me for this talk and all the Serbian group that is organizing this conference. I think with Italy, we have a very strong collaboration and we are growing up a lot of activity, especially for young researchers. And also I want to thank IGF, to which I belong, that allowed this collaboration. So today I want to speak about fatigue assessment of large structures, and I want to speak about some open issues and possible solutions. This is a very important topic because nowadays also large structure and large infrastructure needs fatigue, a proper fatigue design. So some issues. Sorry. So the lecture will be these outlines, and in particular, I will make a bit of introduction. I will speak about the difference between global and local approaches, and after that, I will describe a bit the string energy density volume field procedure that we have developed in the last year and applied to large infrastructure, and some conclusion and remarks. Dealing with increasing complexity in structures, I want to mention that large infrastructure now needs to be designed against fatigue, and the standard reports are requiring this design always even more to be more efficient and more precise. And this is affecting any scale of the structure, from a very large structure to, for example, very small structure. So fatigue is spanning from large pieces of materials to very small materials components. So what we need is the possibility to easily create a complex component, and we need a reduction of wasted materials and an efficient fatigue design for these structures. So another example of large infrastructure that in which I was involved recently was the cover of the Roland Garros stadium, the tennis stadium, that is now is able to close the stadium when, for example, it is raining. And that movement is creating a lot of fatigue issues to the structures. And in that roof, there are almost more than 1,000 weldments to be designed against fatigue. For example, another example together with Cimolai is this large bridge. And I want to mention also that fatigue is a local phenomenon. And we had a very big failure in Norway in 1980, where a large offshore platform collapsed with more than 100 people that died. And this structure was 100 meters in length and collapsed only for the failure of a weld structure that was a few millimeters inside all the structure. So it means that fatigue design is very specific and very local phenomenon that we have to treat with special tools that allows to design the structure properly. So dealing with fatigue in mechanical components, of course, what we are saying for welded structures is also important for innovative materials, because we have the same identical problem, for example, in additive manufacturing, where we have cold cracks, lack of penetration, lack of fusion, inclusion, and pores that strongly affect the fatigue behavior of additive manufactured components. And so everything can be actually translated to those materials as well. Dealing with fatigue assessment through standards, I was involved, for example, in Eurocode 3, and we are almost 30 or 40 years behind the current research. So we are still designing components using a nominal approach, which are really, really conservative and bad in terms of fatigue prediction. So we are overestimating the fatigue behavior of large structures, and it is very difficult to find the categories of the joint that we want to design inside the Eurocode. It's almost impossible. If you have a complex structure, like, for example, the Roland Garros roof, all the welded components inside the structure are not belonging to any category of Eurocode Eurocode 3. Okay? And also we have a lot of simplification and corrections that are mainly empirical and are depending on the geometrical parameters of the structure. This is strongly inefficient and can create a lot of issues. I mean, global methods are, of course, widely appreciated because they are easy to be applied, but of course, they have a lot of limitation because they are not considering the local geometry of the structure. I want to mention also that what we can do with the new local approaches is completely different. Of course, we need much more information for the application of the approach. We need to know the local geometry of the structure, but we have an accurate prediction that is independent on the material, and we are able to also to consider the real local geometry in a proper way. I want also to mention that these local approaches were born mainly in Italy and still in United Kingdom and, for example, in Norway, they are using hotspot methods that are like in the cavern areas with respect to local approaches, because actually we are almost neglecting all what is happening in the hotspot areas of the structures. Dealing with local approaches, I want to mention some recent finding about the strain energy density approach and how we have used this approach for predicting the fatigue behavior of large infrastructure. I will not go inside the theoretical model for, of course, lack of time, but we have developed a method that is able to assess the fatigue failure of components based on the strain of the local strain energy density that is present at the weld toe or weld root of structures. And we were able to summarize all the fatigue data present in the literature, creating a master root that is now containing more than 1,000 fatigue data from welded structures. Which is the advantage of this approach? The advantage of this approach is that you are able to consider the real local geometry of the structures, and this is also valid, for example, if you have additive manufacturing components. You are able to consider all the defects and also the non-homogeneities of the structures, and you are able to import directly the model from for example, a scan model that we obtain from a real three-dimensional structure and obtain the final results with the coarse mesh. The method is very sensitive and also sensitive to the mean stress effect. So we are able to take into account the load ratio effect. That is an important parameter affecting the fatigue life of welded structures. This is an example where we have summarized more than 200 data from titanium alloys, and where we made data from different mean stress under multi-axial loading conditions, and we summarize everything in the same scatter band with the approach that is proving to be able to take into account the nominal load ratio as well. If you consider the standard in force, especially for welded structure, we have Eurocode, British Standard, the NVGL, and International Institute of Welding suggestions. What it is, the deficiency of these approaches is what I mentioned before. We are, in the majority of the case, over-conservative in the fatigue prediction. And second point, actually it's difficult to find the category of the joint inside the standard, because in large infrastructure, for example, in tubular or offshore infrastructure, no one of the joints is belonging to the category that are summarized in the standards. What we have done was to compare different standards together, for example, Eurocode, the NVGL, and other standards, and try to apply the local strain energy density, which is represented by the red line in this three-dimensional graph. So you can see that in some cases, the standards are over-conservative. In other cases, they are not conservative at all. And so actually the local approach is able to find a compromise between all the standard in force with an efficient design of the welded structures. Is also the local approach is also able to detect if the failure will happen, for example, at the root or at the weld toe, things that is quite difficult to do with the standard in force based on the nominal local stress. We have also applied the strain energy density approach to, for example, turbine blades. And we have applied the method to different kind of loading and also multi-axial condition, showing that we were able to summarize the same, all the data from different loading conditions in the same scatter bank after we define the critical radius or the critical material properties for this welded structure. Not okay. Yeah. So what I mentioned before is that if you consider the defects that we have in additive manufacturing, actually we are able to reproduce a structure, for example, with the 3D scan or with the complete tomography of the structure, and after that import the model with the correct dimension of the defect and size inside the finite element method, and apply with the force mesh the strain energy density approach that is able to predict the final fatigue failure. We are working on this topic quite consistently now. I want to mention that one of the limitations of our local approach, which is the strain energy density approach, is the capacity of meshing the structure without considering the volume. What we have done actually was to create a method that is now volume free. So we are able to have the value of the strain energy density only from some elements in front of your critical parts without the necessity of modeling in reality the control radius and control volume in the proximity of the notch discontinuity or crack or defect. So this makes the approach very efficient, and actually we can solve the problem with the force mesh. We have validated this method with many cases, showing the small difference and discrepancies with the fine mesh. So we have actually dealing with the more complex components, the possibility to have force mesh becomes fundamental to reduce the computational amount of cost that we need to solve the model. And in fact, if you consider, for example, these extreme meshes where we have thousands of elements inside the control volume and a few elements inside the other volume, we have only the difference of 2% in the strain energy density. This means that actually the model is very accurate also with force meshes. The target is then to overcome the problem of complex meshes, avoid the mesh refinement, and avoid double simulation to take into account stress singularities. The advantages is that we are able to automatically have a topology optimization of the structure that is very efficient, for example, for additive manufacturing components or 3D printing, a simpler and more efficient models, and the easier applications of the approach. We have applied this method to the design of the Panama gates. That was a large project that was developed between 2013 to 2020 together with an industry that is called Cimolai in Italy. They have designed the 8 Panama gates that are now present in the Panama Channel. And in that case, we had a lot of issues because they want the fatigue prediction of each weldment, and every gate had around 1 million weldments and more than 100,000 notches. So we developed an artificial intelligence or a machine learning approach based on the strain energy density to automatically compute the fatigue assessment of the structures. I cannot give much details about the software, that is the intellectual property of the industry, but actually they are using this software to design complex structures. The advantage of the software is that is able to recognize previous design weldments and is able to avoid unuseful calculation when it finds the similar geometry that he has already calculated. So is able to optimize and efficiently compute a lot of welded structure in one afternoon, for example. So you can, if you want a comparison, you can think that the most critical welded joints of this structure were designed by common engineers with common tools in 6 months for one gate. And now we are able to solve the whole gate in from 1 to 3 hours of computational time. And another work where I was involved were the Mose gates, and in particular the largest gates, which is the Malamocco gate, that has the same issue of the Panama Gate. And also this project is a running project that will be present at the Association of Maritime Engineering and Offshore Structure in Italy, in Catania, in the next January. Another important thing that I mentioned is that data-driven methods or machine learning approach are becoming powerful nowadays. And in particular, we can use them in 2 different directions. We can use them for structure to property design. So it is called forward design. So given a design structure, we can extract the property of the structure. Or the most interesting aspect is that we can also, having some target properties that we want to reach, we can actually obtain the geometrical feature that is able to give us these targeted properties. And this is called inverse design. 95% of the studies up to now are only with structure property design, and we have still to exploit a lot about the inverse design that is still at the beginning phase of this approach. I want to mention that this is studied intensively in our recent finance project ERC Advanced Grant, where we are trying to take inspiration by nature to model super resistant fatigue structures. I want also to mention that some preliminary results of this structure at different scales have been already present, and in particular we are able to model the strength toughness paradox, taking inspiration by nature. This is a paper in collaboration with Robert Ritchie, where we have taken inspiration from different natural structures, and we have 3D printed infiltrate titanium scaffold with magnesium to find innovative, to increase in parallel strength and toughness that are usually conflictual properties, and that are able in this way to increase in both sides. In fact, we are able to control the crack initiation and propagation of the structure, and we are able actually to drive the crack path to the final failure as we want with this kind of structure. This allows to design a new generation of materials, and the aim of a Butterfly, which is my project under fatigue design, is the same, but taking inspiration by nature under fatigue loading, we want actually to design new fatigue super resistant structure, and this is what we are doing nowadays within this project. So you will see some results of this project published soon. Finally, I want to give some conclusion. I think I stay inside my schedule time. We give a comparison between global and local approaches. We explain the advantages of local approach with respect to global approaches, and in particular the advantage of energy-based approach that allows to use force matches to be efficient with the computational models. And after that, a practical way to simplify the procedure of the strain energy density without modeling the volume. And some insight, and I mean philosophical discussion about future possibilities, about topics linked to machine learning applied to material design and structure with inverse design. So I want to thank you for your attention. I want to thank also Pietro Cotti that helped me with this presentation.